Last session we started a difference between core type transformer and shell type transformer. We explained so many points. In addition to that, some more points will come here that we'll discuss now. And one more thing also we'll see. Let me complete this difference between core type and shell type remaining points, and plus advantage of placing low voltage winding near to transformer core. This topic also we'll see. So before going to next points which I want to discuss, I think in the last session I just told how can you reduce leakage flux by considering window factor. See, generally in core type transformer leakage flux will be more, in shell type leakage flux will be less, because in shell type winding sections are more. Each LV is surrounded by two HVs and each HV is surrounded by two LVs. Therefore, there are a lot of chances for having leakage flux to interact with both windings. Thereby, leakage flux will be reduced. That's why I told you leakage flux is less here, more here. Though it is less, I cannot prefer for electrical application, because maintaining your windings is very difficult, because windings are surrounded by core. But whereas here, though leakage flux is more, so I'll be using generally core type transformer only for I can say that electrical applications. The reason is very simple. So here maintenance is very easy, and since we are using core type transformer for electrical application, so though leakage flux is more, I can reduce that leakage flux to some extent by considering window factor. Window factor equals to height of the window by width of the window. So here if you increase height of the window, obviously, so I can say window factor will be more. For core type transformer, window factor will be more, means indirectly I told you window factor more we are keeping. That means what? We are keeping more height of the window. Height I am just keeping more, width I am just keeping less. Why I am just keeping like that means, this height is nothing but, this height is nothing but length of the path for leakage flux. This leakage flux is linking with only this winding, it will not come to this side. Similarly, this leakage flux will link with only this winding, it will not come to this side. So indirectly, height of the window means length of the path of your leakage flux. If you keep more height, that means if you keep more window factor, that means if you keep more height, indirectly you are reducing length of the path for leakage flux you are increasing. Thereby reluctance for leakage flux will increase. Thereby leakage flux will reduce. So like that I can reduce leakage flux by considering window factor, that too by keeping more height and by keeping less width, nothing but by having more window factor. Some people will think, sir, let me keep more height. Let me keep more height so that I can reduce leakage flux a lot. No, that is different case. See, if you keep more height like this, if I keep more height, this is your height of the window, and if you keep like this, if you keep more height like this, what will happen here? Observe clearly. If you keep more height, okay, obviously you are keeping more height means length of the path for leakage flux increases. Whenever L is increases, SL will increase, so that leakage flux will reduce. That is okay. But what will happen to your main flux? That is very important. No? That is also very important, because main flux will flow from here to here to here and from here to here. That means because of keeping more height here, length of the path for your core flux also increasing. Whenever length increases for main flux, reluctance will be more for your core flux. That means your core flux will reduce, which is not desirable. So you should keep more height, but don't keep very large, okay, because for that one I had given some range. Window factor should not be more than 4. Height of the window is maximum 4 times the width of the window. Don't go beyond that. If you go beyond that, what will happen? Your useful flux, or I can say your core flux, will reduce, which is not desirable. That you should remember, okay. Next, in addition to these points, so obviously I can give one more point in core type transformer. Nothing but I already told you core type transformer is economical for what? High voltage low current applications. You please try to try to see your previous session notes. There I told you core type transformer is economical for okay, high voltage, I can say large voltage, economical for large voltage, small current applications. This is already given. In addition to this, we are adding one more thing. It is economical for large voltage, small current, large kVA rating applications. Large kVA rating applications. Please remember this. And shell type transformer is economical for. It is economical for no small voltage, large current, small kVA rating applications, small kVA rating applications. This you have to remember. And in addition to this, some more points we are going to discuss here. What is that? What are those points we are going to discuss here? See guys, here, yes. I think once again, you please try to refer your previous notes where I told one thing I told there. If I place two windings LV and HV on one limb, if I place two windings LV, HV on one limb, let me repeat. If I place two windings LV, HV on one limb to satisfy Lenz's law, direction of current in both windings is opposite. Whenever direction of current is opposite in two windings, we are going to have what are the forces we are going to have? Repulsive forces. Means like this. You are placing winding on this limb, repulsive force means like this will be there. Please try to see Lorentz force law. One topic is there. There I told clearly about this thing. Attractive forces, repulsive forces. If I place windings on two separate limbs, what are the forces we are going to have between those two windings? What is the direction of current in both windings? If I place two windings on same limb, what are the forces we are going to have between those two windings? And what is the direction of current in both windings? These things I explained already in previous session. Please try to see there. Now here conclusion I can say that since windings are placed on one limb, you will be having a direction of current will be opposite and a repulsive force will be there. Yes, repulsive like this. Okay. See repulsive is just like this. You observe clearly these repulsive forces are perpendicular to this limb. Is it correct or not? This is what your limb on which you just place your windings. Okay, this is what your limb. This is perpendicular to your limb. Okay. So see here I can write one point. In core type transformer, under normal condition means I am saying forces point of view. I told you already guys, forces will be always from strong to weak. It depends on strong flux to weak flux. Normal condition means if N1I1 equals to N2I2. Did you remember this condition? If I keep this condition, pi 1, pi 2 dash and pi 2 will cancel with each other. Core flux only pi will be there, that I told. Okay, transformer is constant flux device there. So normal condition N1I1 equals to N2I2. You will be have which forces? Radial forces exist. Radial force exists and they are equal. Equal and opposite direction. They are equal and opposite direction. They are equal and in opposite direction If they are equal and opposite, if they are equal and in opposite direction, what is the resultant force? Therefore, resultant force is equal to 0. Whenever resultant force is not there, windings will not shift. If resultant force is there, windings will shift in a resultant force direction. Here resultant force equals to 0. So that windings will not shift. Okay. Next, what about in shell type transformer, guys? Shell type transformer. To be frank, it is not exactly shell type. You can use one word before that. It's a symmetrical shell type transformer. What is this? Symmetrical shell type transformer. How can you decide that it is a symmetrical shell type transformer? Means very simple. Here extreme ends, if you see here 50% of low voltage sections will be there. 50% of low voltage sections will be placed on top side and bottom side. That is indication that it is a symmetrical shell type transformer. I'll tell you why we are using symmetrical shell type transformer. What are the problems in a asymmetrical configuration of shell type transformer? That also we'll see. But as of now, this is a symmetrical shell type transformer. If you want, you can keep heading also here. Before shell type, you can write symmetrical also. Nothing wrong. Now, in symmetrical shell type transformer, you can write here. Yeah, in symmetrical shell type transformer, transformer under normal condition means what? N1I1 is equals to N2I2 and normal condition. Here also you just observe clearly, this is your limb, this is your middle limb. We are placing windings here. On this limb we are having both LV and HV, both limbs are there. If I place two windings on same limb, you know, I told you repulsive force will be there. Please try to refer that notes. Repulsive force means it will be like this. Repulsive force will be like this, okay? It will be like this. Repulsive force will be there. You tell me these forces are acting parallel to this limb or perpendicular to this limb. This is the middle limb where you are placing windings. These forces acting parallel to this limb are perpendicular to this limb, parallel. So these forces can be called as, you know, parallel forces, or I can say axial forces. Axial forces. Just like in core type, here you are going to have radial forces. They are equal and opposite. Resultant force equal to 0. Here also under normal condition, axial force will come into picture and they are equal in opposite direction. Resultant force equal to 0. So in symmetrical shell type configuration, in symmetrical shell type transformer, under normal condition, N1I1 equals to N2I2, N1I1 equals to N2I2. Okay. Axial force, I can write here. Axial forces exist and they are equal and in opposite direction. Thereby resultant force equals how much? Resultant force equal to 0. Resultant force will equal to 0. Okay, very important. Please try to remember here. This concept, this thing will not happen. Whatever I said, normal condition, N1 equals to N2I2, axial force exists and they are equal and in opposite direction. Resultant force equal to 0. This will not happen in a asymmetrical configuration. There under normal condition also, though N1I1 equals to N2I2, resultant force will come into picture, windings will shift in a resultant force direction. That is a drawback. That's why here is symmetrical. Tell me, in symmetrical under normal condition, if N1I1 equals to N2I2, do you have any resultant forces here? No. Do you have any, winding shifting concept? No here. But in asymmetrical configuration, that will happen under normal condition also. That we'll discuss. Before that, see, and here core type, and one more thing. What is this? Shell type transformer. Core type, shell type. So please write here. I told you under core type transformer, in core type transformer, under normal condition, radial force exists, What is the other name for radial forces? Radial forces, radial forces also called as what? Perpendicular forces, perpendicular forces. Why? Since they are perpendicular to the limb, perpendicular to the limb, perpendicular to the limb on which windings are placed, windings are placed. Similarly here, you are going to have axial forces are there, no? Normal condition. Axial forces can also be called as axial forces, also called as parallel forces, parallel forces. What is the reason? Since they are parallel to the limb, parallel to the limb on which windings are placed, okay. This is the case under normal condition. You said resistance force equal to 0. Under normal condition, total resistance force equal to 0. Very good. Now, what about under abnormal condition? Abnormal condition means what? See here, under abnormal condition means N1 I1 not equal to N2 I2. Suppose I am saying if this thing will happen, don't think how it will happen. I'm saying if this thing will happen, N1 I1 not equal to N2 I2 under abnormal condition. Generally under normal condition, what are the force you are going to have in co-type transformer? What are the force you are going to have under normal condition? Radial forces. Okay. Under abnormal condition, in addition to radial forces, axial forces will come, comma, resultant force is in axial direction. Are you getting my question? So in addition to radial, I'm saying, so you will be having somewhat almost all parallel to your core, almost all parallel to your transformer core. Okay, these are nothing but radial forces. Under abnormal condition, in addition to radial forces, we are going to have axial force will come into picture. So resultant force will be in axial direction. So resultant force is the axial direction, comma, windings shift in axial direction. This is the thing happening. What about here? Here also once again, under abnormal condition, once again, N1 I1 not equal to N2 I2. In addition to, tell me what are the forces generally will be having in a shell type transformer? Axial. In addition to that, what we are going to have? Radial. Okay. In addition to axial forces, radial force exists. Radial force will come. Okay. Comma. Resultant force is in radial direction, comma, windings shift in radial direction. Okay. Are you getting my question? See, under abnormal condition, windings are shifting in a resultant force direction. Maybe that resultant force is nothing but in core type, resultant force under abnormal condition is axial direction. In shell type, under abnormal condition, resultant force is in a radial direction. In that resultant force direction, your windings will shift. Okay, please note. Next, let me give one small note here. Note. So you are saying that under abnormal condition, your windings are shifting in a resultant force direction. So for that, what you have to do? You can give some note here. To avoid, you can write here, to avoid shifting of windings, under abnormal condition, to avoid shifting of windings under abnormal condition, So tell me in which direction your windings are shifting in a resultant force direction. Okay. To avoid shifting of windings and abnormal condition in the direction of resultant force direction, what we have to do? Are you getting my question? To avoid shifting of windings under abnormal condition in a resultant force direction, what we have to do? Okay. Provide steel channels for windings, provide steel channels to windings, I can say. Provide steel channels to windings for mechanical support. So if you observe in a real-time application also, if you take core-type transformer, their windings they will be placing in a steel channels. Steel channels will be there. In the steel channels they will be placing windings, so that under abnormal conditions your windings will not shift in a resultant force direction. Okay, just note on this note. Right. See here, you can write one more note, or you can write in core type and shell type separately. It's your wish. In core type transformer, shape of laminations are I shape, L shape, and U shape. I shape, L shape, and U shape. I shape, L shape, U shape. Whereas in shell type transformer, shape of laminations are I shape, I can say E shape, E shape. Okay, like the H shape, so many things are there. It's not necessary for us. So please note down I, L, U shape, here I shape, E shape. Right. Now, so why we are writing here symmetrical shell type transformer? That means you are having some problem in asymmetric configuration. That's why we are going for symmetrical configuration. So let us see here what is the disadvantage of asymmetrical configuration of shell type transformer. What is the disadvantage of asymmetrical configuration shell type transformer? See, there is no need to draw entire diagram. So simple, actually, I'm just drawing this portion only. This portion only I'm just drawing. Huh? So like that, this side also will be there. I just drawn only one small section. I mean, this section I will take. There is no need to draw the diagram once again. Asymmetrical means it will be like this. Here, tell me how many sections are there? HV1, HV2, HV3. 3 HV sections are there. Here, LV1, 2, LV3 by 2, LV3 by 2. 3 LV sections are there. So I'll take here HV, HV1, LV1, HV2, LV2, okay, HV3 and LV3. So here you know this is nothing but insulation between LV and HVs. HV1, LV1, HV2, LV2, HV3, LV3. Here means how many HVs? 1, 2, 3. How many LVs? 1, 2, 3. It's not compulsory that only 3, 3 like that. In my example, I take like this. Okay. Now observe clearly, guys. Observe clearly. We know we had taken LV. Okay. See, in this asymmetrical, in the name itself, it indicates. Generally, in asymmetric configuration, under normal condition, under normal condition means, actually you tell me, under normal condition, in case of while previously I just told difference between core and the shell, there I told you, under normal condition, do we have any resultant forces? No. In abnormal, that will come, that is okay. I am asking you, under normal condition, in case of your symmetrical configured shell type transformer, do we have any resultant forces? No. But here, under normal condition also, resultant force will come into picture. How means, you observe clearly, you just take exactly middle portion of this configuration, middle portion I'm asking you middle portion, right? Middle portion means, can I take like this? This is what middle portion, exact middle portion. Tell me, here in this side, 2 HV sections are there, 1 LV is there. Here, 2 LVs and 1 HV is there. 2 LVs and 1 HV is there. That means, see, voltage is not, symmetrically distributed. It is not symmetrically distributed. You know, EMF is proposed number of turns. That means number of turns are also not symmetrically distributed here. It is not symmetrically distributed. So I can write here, under normal condition also, number of turns are not symmetrically distributed. Under normal condition also, number of turns are not symmetrically distributed. That is N1I1 not equal to N2I2 will occur. Generally, I told you when this will occur, under abnormal. But here under normal also, this thing is happening. So that is N1I1 not equal to N2I2 will occur. Thereby resultant forces will come and windings shift in resultant force direction. That is the problem in asymmetric configuration of shell type transformer. Now can you please let me discuss how we are overcoming this problem in symmetrical configuration of shell type transformer. See, if you take the symmetrical configuration of shell type transformer, symmetrical configuration of shell type transformer means very simple. Symmetrical configuration means this section. I'm saying this section. I'm just redrawing. Means extreme ends should be having half of LV, half of LV like that. Okay. So I'm just redrawing this here once again. So first of all, you are having what? LV3 by 2. Next HV1, HV1. Next LV1, HV2, LV2. Okay, HV3, LV3 by 2. LV3 by 2. Observe clearly. This is what I can say. LV3 by 2. Here LV3 by 2. Remaining as it is. Means what? HV1, LV1, HV2, LV2, HV3. Whatever this extreme low voltage winding is there, in a asymmetric configuration, whatever the extreme low voltage winding is there, that has taken 50% of extreme low voltage winding is placed on top side, remaining 50% is placed on bottom side. That is only symmetric configuration. I can write it clearly. In symmetric configuration, extreme, 50% of extreme low voltage winding is placed on top side, and remaining 50% and remaining 50% of extreme low voltage winding is placed on bottom side. You make a doubt. So then do you think that here turns are equally distributed? Yes, obviously. How? You can check here. Tell me what is the middle point here? What is the middle, exact portion, exact middle portion? So LV, LV, this HV, whatever it is there, like this. So if you want, I can provide this insulation also between LV3 by 2 HV. HV and LV insulated material is there. LV and HV insulation is there. And here also insulation will be there. Here also insulation will be there. Here also insulation will be there. Okay. Now tell me, this is exact middle portion. Now tell me here. See, if you observe clearly here, HV 2, 1.5 HV I can say. HV here half. I can say what about LV? LV is also 1.5 I can say. What about this side? Half HV. Here 1 HV. Means what? 1.5 HV. And what about LV is 1.5. 1.5 LV. So observe clearly, I can write here. Here what will happen? Under normal conditions, same whatever thing I told here, this statement I am writing here. Under normal condition, number of turns are symmetric. Here are not previously. Now number of turns are symmetrically distributed. Symmetrically distributed. That is, N1 I1 is equals to N2 I2 will occur. Whenever N1 I1 equals to N2 I2, do we have any resultant forces here? No. Therefore, resultant force equals to 0, comma, windings will shift or will not shift? Windings will not shift in normal condition. Windings will not shift in a normal condition. So tell me, in a symmetrical shell type transformer, how we have to find out that it is a symmetrical configuration of shell type transformer? Very simple. Tell me, in this example, how many high voltage sections are there? 1. For enter I'm saying. For how many high voltage sections are there? 1, 2, 3. How many low voltage sections are there after placing 50% of LV in the top side and bottom side? 1, 2, 3, 4. Means for 3 high voltage sections, we are getting 4 low voltage sections. So in symmetrical means for n high voltage sections, n plus 1 low voltage sections will be there. N plus 1 low voltage sections, n plus 1 low voltage sections will present. N plus 1 low voltage sections will present. Is it clear? Just note down. Right. Next, we'll go for our next topic. Nothing but advantage of placing low voltage winding near to transformer core. Near to transformer core. Near to transformer core. So guys, what is our next topic? Advantage of placing, this one is completed. Difference between core and shell completed. I'm just going for this topic. Okay. Advantage of placing low voltage winding near to transformer core. Near to transformer core. See, first we'll see placing a low voltage winding. Placing low voltage winding near to transformer core will take. Next, here we will see placing a high voltage winding near to transformer core. We'll see near to transformer core. We'll see here. So, example. Let me take you know 3.3 kV by 11 kV transformer. Example. Let me take this 3.3 kV by 11 kV transformer. It is what low voltage winding and it is high voltage winding. Suppose if I place low voltage, it is nothing but core. If I place low voltage winding near to transformer core, this is what low voltage winding. How much? No, 3.3 kV LV. I can say 3.3 kV. And this is what insulation. And this is what I can say high voltage winding. Nothing but 11 kV. 11 kV and this is 3.3 kV. Tell me here how much insulation required here for this example. Tell me how much insulation I have to provide means this is 3.3. This let me take core as 0 potential 3.3 0. Difference how much 3.3. So I require 3.3 kV. I require some insulation correspond to 3.3 kV in this region. And I require in this region I require how much insulation required here? 11 is the 11 kV is the high voltage winding. This low voltage winding is 3.3 kV. 11 minus 3.3. 11 minus 3.3. I can say that 7.7. No. Okay, 7.7 kV. I mean, approximately. Right. 7.7 kV. Now tell me total. How much I required? 7.7 plus 3.3. How much once again? 11 kV. So I require insulation I require correspond to 11 kV only. But suppose if you place high voltage winding near transformer core like this is what core, and if I place here high voltage winding like this, and this is insulation, and this is low voltage winding, So here 11 kV and here 3.3 kV. Now tell me here how much insulation required. Here it is 11 kV, it is 0 potential, 11 difference 0, 11 kV plus. Here 11 kV is the high voltage winding, 3.3 kV is the low voltage winding. So obviously I require here 7.7 kV, difference 7.7 kV. Total how much? Observe kV, 18.7 kV. I require insulation corresponding to total. I require insulation corresponding to 18.7 kV. I require insulation corresponding to 18.7 kV. So our heading, advantage of placing low voltage winding near to transformer core. First advantage. What is that? First advantage. If I place low voltage winding near to transformer core, okay, it requires less amount of insulation. It requires less amount of insulation. Next, second one. You want to tell me, suppose here overall requirement of insulation is less here when compared with this case. Whenever thickness of insulation is less, requirement of your copper material also will be less. Whenever requirement of copper material is less, size will reduce, cost will reduce. But whereas here, so thickness of insulation is more because I require insulation corresponding to 18.7 kV. Whenever thickness increases, requirement of copper material also increases. So size increases, cost increases in this case. But here, so since the requirement of insulation is less, thickness of insulation is less, requirement of copper material is less, size reduces, cost reduces. Let me write here. Here thickness of insulation is less, comma, requirement of copper material is less, comma, size reduces, comma, cost reduces. In addition to this third point is very, very important. What is that? See, generally we will take tappings. For selection of your voltage. Okay. Always we will take tappings from high voltage winding, guys. Just listen carefully. High voltage winding, wherever it is there we have to take tappings generally. Okay. High voltage, because it's not high voltage winding. Generally, I am saying, suppose example, if core is like this. To this core, which one is placed near to the core? Near to the core, I just placed a low voltage winding. Near to transformer core. And what high voltage winding 11 kV is outside your transformer core. It is outside of your transformer core. Here to this core, I can say that high voltage is near to the transformer core. Here it is outside. So always it is convenient to take tappings from a winding which is outside. Always it is convenient to take tapping from a winding which is outside. In this case, outside winding is which one? High voltage winding. If you take tappings, if you are changing tapping position from one position to other position, high voltage winding, voltage high, current will be less. While changing tapping position, sparking will be less because of low current. In this case, what is the winding? Is away from the transformer core. Means always it is convenient to take tappings from a winding which is away from transformer core. Here it is a low voltage winding. It is high voltage, it is low voltage. If you take tappings from low voltage winding, if you change tappings from one position to another position, okay, low voltage will be less, current will be more, sparking will be more. Okay, so let me write here. Generally it is convenient to take tappings from a winding which is away from transformer core. What is our heading? Advantage of placing low voltage winding. We are placing low voltage near to the transformer core. That means high voltage winding is away from the transformer core. Therefore, in this case, in this case means what? In this case means what here? LV near to transformer core. In this case means what? LV winding near to transformer core. In this case, high voltage HV winding is away from transformer core, taking tappings from high voltage winding leads to less sparking. What is the reason? Since current is less in high voltage winding. Simple reason. Always it is convenient to take tappings from a winding which is away from the transformer core. If I place low voltage winding near transformer core, what is the winding away from the transformer core? High voltage winding. If we take tappings from high voltage winding, sparking will be less because current is less. Simple. Suppose if you take here, what is the winding away from transformer core? Low voltage winding. If we take tappings in low voltage winding, obviously current will be more, sparking will be more. So please don't, always we should not prefer this one. We have to prefer this one. Okay. So advantages I had given here. Please note.